we studied atmospheric refraction and total internal reflection in the previous video. Now, let's understand a new branch of optics in which we are not taking light as one single wave, because light essentially is composed of many kinds of colors: violet, blue, yellow, and all these colors are actually different waves. And when I say white light, I have all those waves, but those wavelengths vary very slightly, the visible range wavelength. So practically speaking, it doesn't make much of a difference, and so we kind of ignore them in usual circumstances. But sometimes it actually plays a big role. Let's try to understand where it could affect us. Let's think of a prism. This is a prism. Angle of the prism can be thought of as a capital A. If you pass a ray like this incident on the first surface, draw a normal over here. This becomes your angle of incidence, I. Similarly, what will happen is, as all the discussion earlier, this is the original path, but light is not going to go in the original path. It is going to be deviated from this path, refracted essentially. So let's say the light follows this path towards the normal, which makes perfect sense. This is vacuum or air, and this is material of mu, right? So it would be towards the normal, practically speaking. But the moment it reaches over here, again draw a normal. What you would see is that this would bend away from the normal. Why? Because now this is from denser to rarer. Whenever it's from denser to rarer, it is bending away from the normal. Now just produce it backwards. This guy over here, this angle, big angle, is known as delta. And this delta is your angle of deviation. Why is it angular deviation? Because light was actually traveling along this path. But after the final refraction, it is this which is the actual path. So this is your deviation, or the angle of deviation, simply speaking. Now, this angle is the angle with the normal which the refracted ray is making. I can simply say this is angle of emergence or I prime, right? This is angle of incidence. This one is angle of refraction. This is angle of emergence, and this is R prime, angle of incidence for the second situation. The reason I am taking R dash, I prime, or R in this situation is because this is kind of a very symmetrical kind of a situation. If I pass a ray of light along this path, this angle of emergence changes to angle of incidence, and this becomes your angle of refraction. So that's why I'm taking the inside thing as R prime and the outside thing as I prime, because I can pass the ray of light across this direction or this direction. Both the things are possible. Now, let's understand how would I find out the value of this delta, angle of deviation. In this quadrilateral, I know that this angle over here is 90 degrees and this is 90 degrees. So sum of these two angles is 180, which means sum of these two angles would also be 180 degrees. So this angle over here is simply 180 degrees minus A. I'll write again for you. These two sum up to be 180, and I know the sum of angles of a quadrilateral is 360 degrees. So this 2 also has to be 180. So this angle is 180 minus A. Now if this is 180 minus A, I'll read out two triangles. The lower triangle is such. This is R, copy it down. This is R prime or R dash, whatever you say this. And this angle over here is 180 degrees minus A. Now the upper triangle, this guy over here. This is your delta, which I am concerned with. This angle and this angle now. If you think it logically, this angle has to be I, vertically opposite angles, and this smaller one is R. So the angle left out is I minus R. So this angle is simply I minus R. Similarly, this angle would be I prime minus R prime. Why? This is I prime. So this big angle over here is your I prime. This smaller is R prime. So this smaller one becomes I prime minus R prime. So I prime minus R prime. Now, this is a linear pair. This plus this. So this angle becomes how much? This becomes 180 degrees minus delta. Now over here in this triangle, I can simply say that R plus R dash or R prime plus 180 degree minus A is equal to 180 degrees. Why? Sum of the angles of a triangle. Now cancel this thing out. What you would get is R plus R dash is equal to simply A. Take this thing over here. Now I have R plus R dash as A. Similarly, I can do the same thing for this triangle too. Let's do that. For this triangle, what I have is 180 degrees minus delta, this angle, plus this one, I minus R, plus this angle, plus I prime minus R prime. This has to be again 180 degrees, sum of the angles of a triangle. Again, this goes away. So what you have is this delta thing taken away, taken that side. So delta becomes I plus I prime minus R plus R prime. Now, this is a relation for R plus R prime. If I just substitute this guy over here, what I would get is delta is equal to I plus I prime minus A, because R plus R prime is A. This is your angle of deviation. I plus I prime minus A. Now, if I change the value of I, my R would change. Similarly, my R prime would change. So my I prime would also change. So I prime is dependent on I. So if I change my I prime would change. So I plus I prime would change. So I plus I prime minus A would change. So delta would change. So my angle of deviation is dependent on I. So if we make it a function of I, a proper function of I, so net this would be dependent on my angle of incidence. Now, I can make that function in such a way that I can find the maxima and minima of that function. I can differentiate it in terms of I. But that would be a very lengthy process and needlessly boring. So let's try to find out a way, a shorter way, a quicker way, so as I get the minima of angle of deviation, minimum angle of deviation. So the heuristic idea is, let's say I for minimum deviation is greater than angle of emergence or I dash or I prime. So if at angle of minimum deviation my I is greater than I prime, what I can do is I can pass the ray of light from this side also and to retrace its path, maintaining the angle of minimum deviation. But right now I prime is the angle which you're concerned with. That is the incident angle. But I have already assumed that the incident angle has to be greater than the emergence angle. So now this has to be accommodated too. And both the things cannot be accommodated, right? Your I has to be either greater than I prime or less than I prime. Both cannot be simultaneously true. So this assumption essentially is wrong. Let's think in the other way. Let's say that I think I should be less than I prime. Now, if I is less than I prime, if I pass my ray of light now backwards, it would retrace again. But your emergence would play the role of angle of incidence. So now the situation would be such that I prime should be less than I. Again, this also falls flat. Even this assumption is incorrect. So by contradiction, I prove that I can neither be greater than I prime or less than I prime. So this gives me the result that only one of the options are left or is left. That is, I is equal to I prime. Because if inequalities are exhausted, the equality thing is left out. So I has to be equal to I prime. Now this is the condition for your angle of minimum deviation. And if I is equal to I prime, it's very obvious that even R would be equal to R prime. So for minimum angle of deviation, R would be equal to R prime, and that R would be how much? A by 2y. For minimum angle of deviation, R is equal to R prime, and I know the sum is A. So it would be A by 2. And how much would be the value of delta? Or rather, I'll write delta M as subscript so as to understand that this minimum angle of deviation is equal to I plus I prime, which is 2I minus A. Now I have angle of incidence as angle of minimum deviation delta subscript M plus A by 2. So I have the value of I have the value of R. I can use my first law of refraction, which says that sine I upon sine R is equal to how much? Mu. This is mu. If I substitute this, what I would get is sine of this angle, delta M plus A by 2 upon sine of A by 2 is equal to mu. Now over this situation, I have not assumed anything. I have not taken any liberty. So this is valid for all values of A. But generally speaking, the angle of prism is taken to be very small. So if A is very small, it doesn't take much of an intellect to understand that your I would also be small. So if A and I are small, your delta M is also small, which means your delta m plus a by 2 are so small, which means these angles can be just thought of as ratio of angles, not ratio of their sine values. Because for small values of angle, angle is almost equal to the sine of that angle expressed in terms of radian. So by that logic, I will have delta m plus a by 2. By a by 2, the 2 thing goes away. So it becomes delta m plus a by a is equal to mu. You may pause it over here and just check the calculation on your own, because this is very easy. Now, if you cross multiply it and rearrange, what you would get is delta m is equal to mu minus 1 multiplied by a, angle of prism. Now, this is dependent on the refractive index of the prism. Perfectly fine. But the idea is, I don't have one single source of light. Light is composed of many waves, and all those waves have different wavelengths. And mu is related to the wavelength of light source in somewhat of an inverse order. How? If you increase lambda, your mu decreases. So if lambda is increased, mu decreases. If mu decreases, your delta m, angle of minimum deviation, also decreases, which means higher lambda, lower angle of minimum deviation. And if you think of light as a combination or rather a mixture of different colors, the visible spectrum has Vibgyor, where all the colors have different wavelengths. Red has the highest wavelength and violet has the lowest wavelength. Beyond this, infrared has more wavelength than red, and before this, ultraviolet, you have ultraviolet before this, has lesser wavelength than violet, which means this is the least wavelength in the visible spectrum, which means delta m would be maximum for this and minimum for red. So if you place a screen over here, all the constituent colors would be deviated by different amounts if you pass the ray in a symmetrical way, such that this is a case of minimum deviation. Then what you would observe is that a screen placed over here would give you violet, indigo, blue, green, yellow, orange, red. Red at the topmost and violet at the bottommost. See, this is not this much of variation. You would never see the variation this wide. It would be a very small variation. I have magnified it for you for proper understanding, which means violet would be maximum deviated and red would be minimum deviated. Now this also forms the basis for your rainbow formation. How? When rainy season comes or whenever you have raindrops in the atmosphere, what happens is ray of light from sun enter the droplets, and when it enter the droplets, it suffers TIR, and those totally internal reflected rays give us dispersion too. So two things happen for rainbow. What happens? In a rainbow, first TIR happens, and that TIR actually induces a dispersion. Essentially, till now I haven't named this thing as dispersion, but splitting of white light into its constituent colors of violet, indigo, blue, green, yellow, orange and red is known as dispersion. So I can just label it over here. This splitting of white light is known as dispersion. So in atmosphere, the drops, the water droplets or rain droplets, they produce TIR also and dispersion also, and they give rise to rainbow formation. And this is how rainbow is formed from two ideas. First is your splitting of white light, because every color has different angle of minimum deviation, and there's a TIR happening inside the droplet. And this very much sums up your refraction and normal refraction. And in the next video, we'll be moving towards refraction due to curved surfaces. Till now, we have been just dealing with flat surfaces. So let's proceed to the refraction for curved surfaces.